the prize in the sky is being able to unify the macro scale events with the quantum level events in general. Like this unification concept is the sort of holy grail of physics, right? Being able to simplify the dynamics of the universe in terms of all scales.
Do we have a single sentence explanation of why that's so hard?
Before you're saying?
Well, no, I'm saying like right now, like why is the unification across the very big and the very small so difficult?
Well, just the unification is just not there yet, I would say. Okay, I don't know. Maybe it seems easy once we achieve it. We don't know, but we don't have it at the moment. What we have is observation of, we talked about before, the radius of the universe. That's a measurement. It's quite uncertain and it has not the best accuracy, but we are talking about 10 to the 26 meters. Okay. That's the visible universe. And we have the size of the proton, the smallest particle in the universe. Yeah, forget about the electron, which is not measurable. Let's take the proton, the other elementary particle. It has a measurable size. And now you have, you compare this size and you get a huge number. Turns out that the horizon, the radius of the universe is 10 to the 40 times bigger than the radius of the proton. And Paul Dirac related this to the relation of the electric force to the gravitational force, which is also a huge number of 40 digits, more or less. Okay. And he said, oh, this is an incredible coincidence. There should be some unknown connection between atomic physics and cosmology. And this is also one of my favorite problems I like to mention. It's an unsolved problem. It's known for almost 100 years or say 80 years, but we don't have a solution. Yeah.
What's the formal name for this problem? It's
called large number hypothesis. So he started from this relation of the electric force and the gravitational force. You said that they had the same structure, the 1/r² law, okay, but with different constants. And it turns out the electric force is incredibly stronger than the gravitational force. Yeah, I mean, just take a magnet. A magnet, the force of that little magnet in your hand overcomes the gravitational force of the entire Earth. So these are the 40 orders of magnitude. And Dirac pondered over this problem already before cosmology started. But of course, when then the first measurements of the universe came out, he said, "Oh wow! There is another occasion. There's another 10 to the 40 in nature. The relation of the horizon of the cosmological horizon to the proton." Yeah. And this is an unsolved problem. It's even more. You can say, okay, many people dismiss it. Could be coincidence. Well, it can be coincidence, but there is a second, evenly stunning coincidence. If you count the number of particles in the universe, more or less, you have an estimate of the mass of the universe, and you have the mass of a proton. And you have 10 to the 80 particles, which is the square of this magic number, 10 to the 40. So, and that means that the size of the proton and the size of the universe and the mass of the proton, these are messages of nature we have to explain. Okay, and we haven't done it yet. So there are many fantasies, people talking about, oh, how could possibly these theories, quarks, gluon, plasma, in the very first seconds relate astrophysics to particle physics? I don't think these are the right ideas. The only smart quantitative idea, not just blah blah. The only quantitative idea is Dirac's large number hypothesis of 1938, but it's unsolved. We don't know how to build a theory around. Yeah.
Okay. Do you think that its solution will be intuitive?
The way you get to solution is probably you need a lot of good intuition. The solution has to be convincing, has to be, of course, also calculations and quantitative predictions, and so you can measure the if it's a successful theory, you need the coincidence of experiment and theory. Okay. Yeah, there is a chapter in my Einstein's Lost Key how to possibly relate Dirac's large number also to this idea of variable speed of light. But yeah,
because it makes sense to me that if what we mean by all of the matter that exists is all of the atoms that we can see, i.e., all of the ones that we're photogravitationally connected to directly or through some relay that we can observe, then you would easily pull out the number of atoms. Well, let's say protons are all atoms are essentially composites of the proton, and
yes.
So you would. I don't know. It just seems like you're basically counting up all of the connections between all of the different atoms, and that their forces are going to be in proportion to their connectivity.
Yeah, like Shiloh and I will sometimes have this conversation where, people use the word universe. And the question is, when you say universe, is it everything or is it everything that you can detect? Because there's something that lies beyond your bubble of vision.
Well, I don't have a different take here. Just I use universe as everyone else does it. I mean, of course, everything we can observe, and we don't know what we will see tomorrow in our telescopes. Maybe some pink elephant will pop up, but it's not likely. So the universe is likely to look very, very, very similar if you observe it tomorrow.
I mean,
what's so
was that
fascinating?
your question, or
no? The question is this: where I'm like, okay, so there is some number of atoms that, if we take light to be a product of connectivity between disparate objects, right?
Well, light's an interaction
a
between.
little problem maybe with that.
Okay.
Phrase. What do you mean by product of connectivity?
So what I would say is that the reason that you can see the light from Vega,
Or just from the light bulb.
or from the light bulb, I mean, for some reason I think about it cosmically, but the reason that you can see the light coming from, here, go.
Well, it's very difficult to imagine light without two atoms. One's an emitter and one's a receiver.
Is there light in a single atom universe? If you take a spherical cow.
I mean, we've been to the bottom of the well with this. People like Carver Mead have gone through quantum electrodynamics and pulled out the math that supports the idea that atoms are undergoing a conversation which is called light. Both atoms are participating in the conversation. And I don't know, what's really interesting to me about this,
nice. I see. Yeah. Mm-hmm.
Yeah. Mm-hmm. And what I wanted to say is what's really interesting is if we define the universe as everything we can see, then talking about the birth of everything we can see is a very rational concept all of a sudden. But talking about the birth of everything that exists being stuff that we can't see too, and just like the appearance of material and stuff gets into a weird supernatural realm. Go ahead, Nancy.
Okay, so the way that I see it is that imagine that there is a mixing constant of the universe, like a diffusion coefficient of how long it takes for stuff that's inside of a sun or inside of a planet to get mixed into the entire galaxy, and then how long it takes for it to get mixed in between galaxies, and how long it takes for it to get mixed out to the very edges of what we can see. What you're really getting from that is you're getting a moment in time where all of the atoms that are now scattered are part of the same body, and they're nearby and they're connected. And as they scatter and mix through the universe, you're getting this sort of almost echolocation of what is out there. But the only things that you can see are the things that have a lot of atoms shared with your origin point however many billions of years ago as part of the diffusion coefficient of all matter.
Okay, there are again a couple of avenues, a couple of different answers. But